Well, you may have read in textbooks this kind of definition for hydrogen bonds, that they're the weak attractions between partially positive hydrogens and partially negative oxygens or nitrogens. You may not really get that because you know what ionic and covalent bonds are, but how does that fit into this? Hydrogen bonds are a weird category bonds all kind of by themselves because unlike ionic or covalent bonds, which hold individual atoms together to form molecules, hydrogen bonds are typically weak attractions between two different molecules that hold those two different molecules close to each other. Now, how does this work? Well, it's all based on this quality that atoms have called electronegativity. In short, electronegativity is essentially how strongly does that atom pull on its electrons. Now, carbon, here I see a methane molecule, CH4, it has roughly the same electronegativity as the hydrogens that are bound to it, indicated by these black lines. Because it has roughly the same electronegativity, the two electrons here that form this bond are shared equally between the carbon and the hydrogen. Same over here. Oxygen, on the other hand, is an electronegative strong one. So it tends to pull the electrons much closer to it and further away from hydrogen, which is too weak to hold on to those electrons very well. So these electrons spend most of their time orbiting around the oxygen, very little time orbiting around the hydrogen. They are essentially only having visitation rights on the weak end as opposed to equal co-rights. So what that means is that these negative electrons tend to spend a little bit more time around the oxygen than around the hydrogen. That makes this oxygen slightly negative. If it's slightly negative, that means this hydrogen here is slightly positive. Now, scientists don't like writing stuff that means it's easy to understand. So they use the Greek letter delta, lowercase delta, to represent this slightly. I've always thought of it as kind of this weirdly cursive S, so I just think sorta. So here's my partially positive hydrogen, or sorta, or slightly positive hydrogen. So slightly positive, wait a second. This is slightly negative, but I know that water is a neutral atom, or neutral molecule, so it's got to be, yes, you guessed it, two slightly negatives. All right? Now, how this comes into play is, here's another water molecule. This is sort of positive, this is sort of positive, this is two sort of negatives, this is sort of positive, this is sort of positive, this is two slightly negatives. So what happens is that as this water molecule is floating around, this water molecule over here, this slightly positive, slightly negative, I'm slightly attracted. You form this weak attraction between these two molecules. Similarly, this water molecule over here, its hydrogen is going, hey, you're sort of attractive, and so we have our weak hydrogen bond there. This is extremely important in many ways because you may think of this as big whoop-de-doo, but it's actually a very big whoop-de-doo in biology because this influences tons of things, especially water. Now, you may have studied water in chemistry and learned about all of its wonderful properties, most of which are due to hydrogen bonding. For example, water is extremely hard to get it to boil. It takes a ton of energy. Why is that? Why does it take so much energy to turn it into a gas? That's because all the other water molecules start trying to cohere, trying to stick to the water molecules that's going away, pulling it back, kind of like molecular Velcro. It's really hard to get it to go away. It takes a ton of energy. This same quality of water, this cohesiveness, is how a tree is able to evaporate water from its leaves, and by cohesion, it's able to pull water molecules all the way down from the bottom of the tree and the roots pulling the water in from the soil. Another ability that water has is adhesion. It tends to stick to things. Here's a standard paper towel. I put it on my hand and it starts to fall. No big deal. Why? Gravity. If I get it wet, on the other hand, add some water. Now, I will show you some magic. Dun, dun, dun. So, same paper towel, all I've done is add water, which should make it heavier so it should fall faster, right? Unless Galileo was right. Wait a second, it's not falling. Well, eventually it does. Why? Did I generate anti-gravity here? Why did it stay? Because of hydrogen bonds. The water molecules were binding and sticking to the molecules that make up the paper towel, and also binding and sticking to my hand, so acting as a molecular glue. Now you may be thinking, okay, so we can do some evaporation stuff. So it's just water? No, it's more. Proteins hydrogen bond all over the place, and this gives them many of their abilities to form different shapes. It even causes the double helix of the DNA to spiral up and hold together. It is involved in so many things that this is a trick that I've taught my AP biology students. Whenever I call them and they don't know the answer, an answer that they can always pull out of their pocket is it's due to hydrogen bonds. And chances are it's right. If your teacher is one of those really annoying teachers who knows lots of stuff and he's really smart and knows a lot, and he calls on you, just say, well, it's probably due to hydrogen bonds. And if he's smart enough, he'll be able to invent a way that, yes, it is due to hydrogen bonds.